Hi, good afternoon. This is a first recording of exam 2 notes. Then I'm gonna talk about the topics that we have on exam 2, and maybe also I'm gonna add some examples. Now, for the topics here of this exam, of course, we are going to have three chapters. First, chapter 24, which is about capacitance and dielectric. And I will say maybe the first note here is going to be about chapter 24. And I'm gonna record also another one for chapter 25 and chapter 26. Chapter 25, it's about current, resistance, and electromotive force. Yeah, this chapter is providing basic information that is going to be used more application in chapter 26, which is chapter 26 will be about direct current circuits. Then we are going to talk about circuits in general, and we are going to talk about how to analyze circuits with resistors and capacitors. The first note here I'm gonna add is you need to know, and this is of course from chapter 24, you need to know how to derive capacitance expressions of different types of capacitors. Of course, we're gonna use for this the general equation Q divided by VAB. Now, one thing I want to say here is, okay, let me add, I need to add a page before. All right, yeah, what I want to say here is what are the different types of capacitors. The first one is the parallel plate. The second one, it is the spherical capacitor. And you have, of course, these derivations as examples in your textbook. The third one, it is the cylindrical. Now, one thing I'm gonna bring to your attention is when you are going to apply the equation above that I shared with you, which is the C equals Q divided by V, you need to find the expression for potential difference or voltage. And these are listed in chapter 23. This is the reason that why I told you, like, I will give you all the equation sheets from the previous chapters, because you might need the VAB expression for different types of conductors where you will be able to use it in this one. Now, note 2 here is when you are going to calculate the equivalent, and of course in the exam for sure you're gonna calculate the equivalent capacitance of a network of capacitors. I want you to remember that. First, one path in a circuit means capacitors are in series, or what we can say, as I did told you in the lecture, in the lab, this is, let's say 1 2, then this is 1 2, then this is how they're gonna be connected. And if you look here, it's only one path, the circuit will not branch. Now the second one here, it is in a series connection, the charge is the same, which means like if I have, this is C1 and C2, we know that is going to be, okay, the same charge. Then here I can say Q1 equals Q2, but of course V1 plus V2 equals a total V. Then it depends on what is really the total voltage, but their charges are really the same. Now, when we're gonna have the circuit, we'll kind of have branches, then the capacitors are in parallel. For example, let's say something like this. All right, then here these are two in parallel. But just remember, if we have something like this, these are in series. Okay, look here what's happening. All right, here the is gonna split and is gonna combine again, but this one, it's not branching, it's the same route. Okay, when capacitors are, okay, this is my, okay, number 3, when capacitors are in parallel, V is the same. Then if I look at these here, V1 and V2, look here, this point is the same as this point, and this point is the same as this point. Therefore, here V1 equals V2. Number 4, you need always, even if the question is not asking, because if I'm asking you to calculate the charge on a capacitor or potential difference, you need to simplify, and this is your first job, to simplify your network to have only one capacitor. which is we call it C equivalent. And then we're gonna calculate usually Q total. And afterwards, what we are going to do is we are going to work backward most of the time. Every time redraw the circuit, and I will show you now an example how to do that. Then work backward to calculate charge of on each capacitor and potential difference across each capacitor. I want to do one of the problems from the homework, which is this one, 59. This one is, like, it's very complicated, I would say, like, or it has so many parts. I will not say complicated. Actually, it has some kind of symmetry that is going to make it, like, sometimes this can simplify the, the calculation. But I mean, it has so many, like, capacitors. All right, in this one here, each capacitance C1 is 6.9 microfarad, and each capacitance C2 is 4.6 microfarads. Then not all the capacitors are the same. All right. The first thing, compute the equivalent capacitance of the network between points A and B, and we need to calculate charges, and then we need to calculate voltages. I will say always when I will do that, like the equivalent capacitance, even if they call them C1, 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 I feel always it's easier for me to say this is C1, this is C2, this is C3, this is C4, this is C5. I will label them C6, C7. All right, then this one C7, and that one is C8, and this one is C9. And my notation that I will use when I will say C1 to 3 means the equivalent capacitance of capacitor C1, C2, and C3. This is the notation that I will use. Now I will say the first step always is to solve for the equivalent capacitance of the whole network. And I will start backward from right to left. All right, then I'm gonna redraw that the last three, which are to the right. All right, and these here, I call these, okay, these are my C3, C4, and C5. Now, if I will look here, there is no branching, and it is only one route. Only one route means series connection. For a series connection, we know, okay, we need to know that Now I will write C3, C4, and C5 are in series. Then 1 over, it's not C35, it is 1 over, equals 1 over C3 plus 1 over C4 plus 1 over C5. Here there is a simplification, I said, because of the values, like some of them are really constant. This is 1 over 6.9, and this one it is 1.6.9, and that one is 1.606 over 9, 6.9, and this is 3 divided by 6, and this is not C, this is 1 over C. And then here, in order for us to calculate C345, you divide this 6.9 microfarad, you flip it, and that is 2.3 microfarad. Actually, when you have 3 resistors or 4 resistors, the same value, not resistors, sorry, capacitors, 3 or 4 of them, they are in series, then the equivalent capacitance is going to be the value divided by their number, the equivalent. All right, now I need to redraw my circuit. I like to do that, although maybe it's gonna take a time, but this is C1, this is C9, this is C2, this is C8, and that one is C345. This is C6, and this one is C7. Now, if you look at C8 and C345, you're going to find them in parallel. C8 and C345 are in parallel. The reason is here the current is gonna branch and then is gonna combine together. All right, then here I will say C3458. The rule, it is you add, it's easier. All right, and therefore this is gonna be 2.3, which we calculated in the previous step, times 6.9, times 4.6, which is the value for the other capacitor, and that is gonna be 6.9. Now, then again, I'm gonna simplify my circuit. All right. This is C2. This one now, it is C3458 and equals 6.9. And here I have also another one, which is C6. This one C9. This is C1, and this one is C7. Now we're gonna go back to series. 3, 4, 5, 8, and C6 are in series. Then we are going to have 1 over C 2, 3, 4, 5, 8, 6. It is 1 over C2 plus 1 over C3, 4, 5, 8 plus 1 over C6. And again, we're gonna go back to 1 over 6.9 plus 1 over 6.9 plus 1 over 6.9, and that is 3 over 6.9, and therefore C23456, it is 6.9 microfarad divided by 3, which is 2.3 microfarad again. Now I can redraw just this part. This is C9, and here I have that capacitor, the equivalent of 2 and 3 and 4 and 5 and 8 and 6. And here I can say C9 and C2, 3, 4, 5, 8, 6 are in parallel. And then here I will say 2, 3, 4, 5, 8, 6, 9. It is C2, 3, 4, 5, 8, 6 plus C9. And again, I have 2.3 microfarad plus 4.6 microfarad, and that equals 6.9. Now, this is the last step in that. I'm gonna redraw C1, and then here I have C2, 3, 4, 5, 8, 6, 9, and these are all in series. And again, we're gonna repeat C equivalent. It is 1 over C1 plus 1 over C7 plus 1 over C2, 3, 4, 5, 8, 6, 9. And I can go again to 2.3 microfarad. Then the equivalent for all these is, okay, my my circuit ended with being only one capacitor, that is 2.3 microfarad. In part B, they are asking what is the charge on each of the 3 capacitors nearest to A and B when VAB equals 420 volts, which means they are looking for this one C1 and C9, of course, like all the circuit is there, and this is C7 when we have here 420 volts. Okay, I'm gonna provide here an alternative solution that is maybe a little bit different from that you have in the manual, because I want to show you for a more general. In the solution manual, they told you because they are really 3 of them are equal, then we know that the voltage is going to divide equally. But what if they are not equal? All right, now I can here from this one, the equivalent, okay, from this one the equivalent, the total, like for the total circuit, and this one is 240. I can say here Q total will be V times C equivalent, and therefore is gonna be 420 times 2.3 microfarad, and that is going to be 966 microcoulomb. As I mentioned in the lab, if we don't have to convert here, we can leave it microcoulomb. And of course, for the sake of significant figures, they're gonna say it is like 97 microcoulomb. Now, after that, like I can go backward from here to here. Not from here to here, sorry. I can go back to the step before this one, which is this one. Okay, let me take this with me. Copy this one, screenshot. Copy this one. And then here, what I can do, I can put this here. And then I have all these capacitors. Each is gonna have, like here, I can say C1, C7, and C2, 3, 4, 5, 8, 6, 9. Each has 966 microcoulomb of charge. Then I know that what is the charge for then Q1 equals Q7 equals 966 microcoulomb. Now what about, okay, now I need to have capacitor just 9 by itself. Now we know that the step before this one here, okay, we have C9 like this, and we have here these two capacitors, 2, 3, 4, 5, 8, 6. This one is, we calculated this one as the equivalent of these two. We know that C2, 3, 4, 5, 8, 6, 9, it is 6.9 microfarad. Then its potential difference is 2, 3, 4, 5, 8, 6, 9. It is a Q of it divided by its C, and that is 966 microcoulomb divided by 6.9 microfarad. And from that, I can get this number to be 140 volts. But if you look at that this one here, you're gonna say, okay, this voltage for this one equals this one. Therefore, I can say that V9 is 140 volts as well. All right, and then the charge on it will be Q9 equals V9 times C9, which means it is 140 times 4.6 microfarad, and that is 644 microcoulomb, which is 64 microcoulomb for the sake of significant figures. For the last part, C, okay, they are asking about the potential difference. The potential difference VCD, and that is actually, if we look here, this is C1, this one is C9, this one is C7, and that one here, it is C2, and here I have this one is C6, and this one here, it is C3468. This is 6.9. And we know that this one, C2, it is 6.9. and we know that this one is 6.9. We know that 140, which equals V9, it equals V2 plus V6 plus C3 force, it plus V3468. Then equal values of C means each will have, okay, 140 volts divided by 3, which is 46.7 volts, which is 47 volts. Then this is an example that I wish is gonna show you how to do these type of circuits. Thank you.